really neat presentation that he's going to present to you today. So I'd like you to all join me in a round of applause for Richard.
From the state-of-the-art of one of the leading technology companies in the world on speech recognition, before deep learning was introduced and after it was introduced. So we'll have to listen carefully here to hear what the presenter, this is also a technology conference and presentation, is saying, and then what the speech recognition system is writing down. Dear mom, comma. Fix ant. Delete that. Delete that. Delete that. Select all. I think it's picking up a little bit echo here. Delete. Select all. So that was in 2006, before deep learning got introduced to speech recognition. Now, the same company in 2012, after they used deep learning for speech recognition, gave the following demonstration.
To the presentations today. 希望今天你喜欢其他的讲座。 Personally, I believe this is going to lead to a better world. 我个人认为这将导致更好的世界。I hope you enjoy the rest of the presentations today. 希望今天你喜欢其他的讲座。
So that was Microsoft, and essentially the difference of understanding natural speech without deep learning and with deep learning. And what's amazing is after they've done that on the research side, really quickly thereafter, it actually became part of real products. And now whenever you talk to your Android or Microsoft phone, you'll actually use a deep learning system to have your speech be understood by the computer. Now, in general, speech is just one example, and I'll actually go and focus more on two others, which are images or visual data and text. But in general, whenever you have unstructured data and you want to extract information out of it, that's when deep learning is likely going to give you huge gains compared to traditional machine learning. Which is fine. In general, anything that traditional machine learning can do, deep learning can do also, but the gains, if you have tabular data, are not quite as high as if you have unstructured kinds of data. Very simple edges that fire. And you might expect to have specific vertical edges seen more often, for instance, in city images versus forest images. But what's interesting is with each layer of these deep architectures, they learn to combine the features to more and more complex visual stimuli, and then in the end actually have nodes that refire when they see shoulders or whole heads, and things like that when it comes to people. So that is how deep learning works on a very, very high level. We could spend many hours on it. In fact, I'm teaching also a class at Stanford on deep learning for natural language processing, so we literally spend an entire quarter on this. Happy to chat a little bit afterwards too. It's also only how it works for computer vision. In natural language processing, it's quite a different story, but there also it can learn a lot of the features. So when you look, for instance, at sentiment analysis, and I'll show you some demos there about that later, you don't have to go in and say, all right, these are the positive words, these are the negative words, and this is how I would negate a positive word, and here's maybe how I amplify positive words and things like that. It just, no more regular expressions are needed, it'll just learn these patterns from your input data. So now, this is a rough overview of how it works and what it does and when you might want to use it, but what's a real use case? So imagine you're running an e-commerce site and you're required to manually label all your user images. You might not want to have not safe for work content land on your front page, for instance. Or you might want to help your users to label images with the right kinds of tags so other people who want to buy the products that the first user is uploading can actually find them. So this would be relatively slow and expensive, and it's often outsourced offshore or into other countries. And so one of the big breakthroughs of deep learning in computer vision is actually that we can now very accurately label images. So let me give you a couple of examples in some live demos. So here's one classifier. It's called the Net Classifier. It's a very large, actually academic data set that enabled the breakthrough on the visual side. And what it essentially allows you to do is classify thousands of different categories, anything from acoustic guitar to an airliner, or apron, artichokes, and so on. A very broad range of different visual classes, and it essentially gives you back the label. And because often most images show multiple objects, it actually gives you back a couple of labels, and the way this is evaluated is usually in terms of top 5 accuracy. So you only need to have the right answer in the top 5 images. So that's just one classifier that is already there, and it works out of the box, but only for these specific 1,000 classes. And it works, again, much more accurately. So the main difference here is really not just in terms of the expert's time, how long it takes them to get to this accuracy, but really the absolute accuracy is much higher. And this is, again, top 5 accuracy. So traditional computer vision methods were in the low 70s, and then deep learning didn't just overtake them by over 10%, but really the speed in which deep learning is progressing is also very high. So in 2012, the accuracy on this famous benchmark data set was 84, and now it's actually in the mid-90s. So why does deep learning work, and why now? I get that question a lot because some of the technology, some of the very low-level algorithms, such as standard neural networks, have actually been around for many decades. The main differences are threefold. The first one is we actually now have large enough data sets. When you require your algorithm to learn the patterns by itself without you giving all your prior knowledge into how negation works or that there should be whiskers when you try to find cat images and things like that, you need to have more data for the algorithm to learn this. It has less prior knowledge. Once you have these very large models that can capture all this information up to very fine-grained details, you then also need to have very fast hardware, and that is basically GPUs on the image side. On the text side, it's at least multi-core CPUs. So GPUs have enabled a lot of the breakthroughs on the visual deep learning side. And then there are actually still a couple of algorithmic advances, and it's hard to pinpoint really a single one because there are lots of small advances that each maybe have given us only 3 to 4%, maybe 5% additional accuracy, but you add 5 or 10 of those, and you actually get into the 90s instead of being stuck in the 70s in terms of your accuracy. And now what I tried to do after my PhD last year is to actually allow you to just, given the data, not have to build a GPU cluster and not have to hire data scientists or deep learning experts who know how to tune these algorithms, and instead have a simple-to-use platform that enables you to use this technology. And I think what's exciting about this is that we try to essentially enable you to create your own classifiers for any kind of visual problem that you might have. And so here are some examples, or here's basically a demo of how easy it is to train something. And the only problem will be if the Wi-Fi is not in our favor. So let me show you some examples here. So let's say you are working in a car company and you want to understand in some marketing, on Twitter for instance, what kinds of images are showing your company cars, and then what do people say about your brand on social media. So here we have essentially a couple of images of Audis, BMWs, and Teslas, and all you need to do to create a classifier that will now automatically find an Audi, BMW, or Tesla car inside millions of other images
is essentially train it. So we have here the training data set, and we drag and drop them in here, and we give it a label. So this is the Audi class. Next class are the BMWs. And again, here we have 13 images of BMWs. And since we're in Silicon Valley, I have a Tesla class. Here again, we have 13 images of Teslas. And now you can give this a name. So this would be our car brands classifier. You can actually be nice and share that data. Of course, most companies wouldn't want to share either the data or the final classifier because it's very core to their IP. And now we click on upload and train, and now these images are sent to the backend, a GPU backend, and basically train the algorithm. The Wi-Fi was in our favor. And so now, basically, these neural networks are trained. There's actually a little bit of a trick going on here, which is this model has seen millions of images before of other classes, and then we do transfer learning and transfer some of the weights and update this model to be specific to your problem. And now, in just a couple of seconds, we have a production level classifier that could go over millions of images and automatically label them for these 3 classes. And all you'd have to do is, use these 3 lines of Python code to make that happen. Now we can test it and by some unseen images from our little test set here and see how it does. So correctly classified this one as a BMW, this one as an Audi, and it gives you the probability. You're also actually able to click here and tell it if it was wrong and try to fix it. If you do that enough, eventually we'll actually upgrade or update the algorithm. Now, if you only give it 13, it doesn't make sense to change the entire network. It only makes sense to change parts of the network. If you actually upload hundreds or thousands of images, you would probably use the API, which is also Python-based or Perl-based. And some of the largest classifiers that users have are, for instance, separating out thousands of different car model makes and years. And those kinds of classifiers would require hundreds of thousands of images. So the drag and drop is more of a fun demo. People have created a whole host of different things, most of which I can't show you because they're private. But here are just some examples of classifying document types based on just the visuals of the scans, planktons, different types, malaria blood samples. In fact, medical is a huge application that we're very excited about, and I'll show you a couple of others in here. Basically, you start seeing this the usefulness of these applications when you see what sort of the ingenuity and the interesting applications that people explore. So this one here is actually an application where marketing, probably interns, have to go through soccer videos and label every frame where you see the specific logo of one of the sponsors. It's a pretty boring task, but it's still possible to do that manually, right? And at the end, you basically say, all right, we paid this much, and this is how much airtime we got from this soccer game. Of course, when you then ask, all right, now do that for every single Flickr and Instagram image, it's basically impossible for any intern army to do that. And this is another application, basically trying to find dozens of different types of company logos in Twitter images, Instagram images. Where I personally think gets really exciting too is in the medical domain. It's a very different type of problem for people. In fact, this is in many cases sort of superhuman accuracy for most of us, because most of us aren't trained radiologists who have gone through 7 years of med school and radiology specialization. But to the algorithm, this is the same thing, just a bunch of images in with one class and then make predictions for them afterwards. And I think this will, in the next couple of years, revolutionize radiology and bring it also into areas that don't currently have access to it. In fact, this is one of the applications that's also pushed us to create on-prem packages so you don't have to have an internet connection, because if you really want to apply these out in the field, you might not have an internet connection. You might want to use it locally. So this one here is, in particular, is a company called CareSharing. They're a European SaaS company that works with diabetes centers, and this is a diabetic retinopathy classifier. It's one of the leading causes of blindness for patients with diabetes. Now, generally, diabetes and obesity are actually big problems too, so one thing we found is that if you have to collect your own data, you can do that if you have some amount of skills and knowledge about the organization and have the right data infrastructure. But in some cases, there are algorithms or classifiers that enough people really want that we actually go ahead and just collect the training data ourselves. And one of these is a food classifier, where we have now hundreds of different food classes and build the most accurate food classifier. So you can imagine you have an app, you want to encourage as a health insurance company your customers to change their eating habits. This will allow you to very quickly sort of take stock of what you eat every day instead of having to type it in manually. Now, I think most companies out there still don't require visual labeling as much as textual understanding. I think pretty much every company out there has to deal with large amounts of text, right? As soon as you have customers, as soon as you have some kind of social media presence, as soon as you have to email, you deal with natural language understanding problems. And that is another domain that is hugely changing right now with deep learning. There are a couple of different applications here that I want to show you and show you the power of what deep learning can do in these. So let's start with social media. So what we've done here is actually combine visual understanding tools and textual understanding tools to predict social media engagement. So before you send out a tweet, this can actually tell you how engaging your tweet will be. So it's almost like an A/B test, but based on all the past history that these algorithms ingested, instead of having to actually use your social capital and run it for real. So here is an example of a tweet that says, take a closer look at the world of Tomorrowland. It's a movie that came out a couple months ago, and an image. And now what we can tell you is that this photo is indeed an engaging photo, at least that's what the algorithm thinks and predicts, but it's actually true in this case. However, the text is not very engaging. And here we actually use a grammatical analysis of the sentence to try to tell you which phrases are the worst or the best in terms of engagement. And one thing we found here is, take a closer look, for instance, is not very helpful when it comes to engaging your users. People don't like to be told what to do on Twitter and maybe anywhere else in the world. So basically, this overall sentence or tweet text is not very engaging, but the image is. And we can also tell you why. You can actually query these, in this case, convolutional neural network models and ask them, why do you think this class is likely? Which pixels of the image are driving this class prediction? And here, it will basically tell you it's a little bit the blonde hair, clothing, and cool-looking buildings in the background that make this picture engaging. And you didn't need to have any eye tracking experiments or anything like that, right? It just takes a lot of images in, makes predictions for them, tries to make very accurate predictions of engagement versus not engaging, above average or below average in engagement, and then you can query the model afterwards and ask it why. The second one is actually also a fun combination of visual and textual modalities. So basically, for deep learning in text and in images, everything is represented as a vector, just a list of numbers. It's a very simple representation, but it's also very powerful. And what we've done here is actually map every word that we type, or every sentence that we type, we map it with a neural network architecture, in this case a recursive neural network, into a vector space. And we trained this model to essentially learn that when you have a certain image and training time, a sentence, you want to map both of these modalities into a vector space such they're close together in that vector space. So you have some high dimensional space, usually around 50 or 100 dimensions, and you use a recursive neural network, give that as input the text, and you have a convolutional neural network, you give it as input the raw pixels, you pipe them through these two deep learning architectures, and you say the output should be close to one another if they're actually describing the same thing. So this is our training data set here. A white colored room with closed blinds, dark sofas, and so on. And now we can basically type in not just a single word. This is kind of similar to the image classification problem on ImageNet, but I can go and type in birds in plural, and the model actually learned that birds in singular look different to multiple birds. And the really cool part is that I can type in whole sentences, type in birds on water, and those look different to birds in trees. So it actually learned the compositional structure of these phrases and sentences and understood sort of the visual meaning of the sentence. There are lots of fun examples. You can have more abstract things like people having fun, different ways that people had fun in the training data set, sort of different types of visual descriptions of that. If you type in just yellow, for instance, it will show you a bunch of random yellow objects, but if you type in yellow bus, actually the closest ones, and this is also related to the distance in the vector space, the high dimensional one, the closest two are actual yellow buses, and then there are only 2 yellow buses in the data set, so the next closest objects are actually other buses and not other random yellow objects. So it also learned that visually the noun, the object, is actually more important than its attributes. And it can get pretty specific, so it can have horse, and just a bunch of horse images, or horse with bald man, and actually found that one image in the data set of a horse with a bald man. And in fact, even the mistakes here are kind of interesting, show you that there's still a lot of work to be done. The other close ones are actually people wearing helmets. So the model makes them look like they're bald. And the last one is email. I can't really show any customers' emails, but basically, imagine you have hundreds of thousands of customer requests in your company, and you get basically somewhat of a power law distribution of some questions that you just get all the time. How do we log in? I forgot my password and stuff like that. Now, if you see the same kind of answer in your database being given to 100 different questions, then that is essentially a text classification problem also. And we have some first experiments that show that really it's quite easy to classify and automatically reply to a lot of emails, and that would make customer support staff much more efficient. So one thing on the research side that I'm the most excited about is actually that we found a model that can deal with any natural language processing problem that can be cast as a question answering problem over some input. And I think actually that is pretty much every NLP problem out there. I'd love for anybody to think of a problem in natural language processing that we couldn't cast as a question answering problem over some input. I have a hard time finding one. And so in the research that we've done at MetaMind, we essentially invented the so-called dynamic memory network. It's a neural network architecture that essentially takes in a question and then conditions an attention mechanism to go over your previous inputs, given this question in mind, and try to reason over it and then create an answer. So let me show you an example here of what this looks like. So here we have a story. This is actually a sample from a data set called the Bobby data set that Facebook published a couple months ago. And we ask, given these inputs here, what color is Bernard? Now, I'm going to give you all a few seconds to try to come up with the answer. Anybody know what the answer should be? Yes, that's right, yellow. And so you might think, okay, how would I do this? Well, the question is about Bernard, so it makes sense to go through, find anything with color of Bernard, and okay, Bernard is a frog. But that doesn't give us the answer. It's not enough information to actually answer this question. So what we might do next is to say, all right, well, if we know Bernard is a frog, then maybe what we should look for is the color of frogs. We do that, but there isn't such a thing, but what we do find is that Lily is a frog. So that's helpful. Maybe now we should look for Lily, frogs, and Bernard. And what we then find is that Lily is yellow. And what's cool is that that is exactly what this model also did. It essentially learned by itself that it needs multiple episodes, multiple passes over the data set to reason over these facts in some transitive fashion. And again, all the model sees are vector representations. This is the story that you read to the model. There are no regular expressions. You don't need to say, these are the lists of colors, and these are the lists of people, and this is how you do transitive reasoning. You just give it a lot of examples of, here's a story, here's a question, and this is the right answer. You figure out how to get to that right answer, and then after you give it enough of those kinds of stories and this kind of reasoning, you'll be able to generalize to unseen stories. So that is one example. Now, you would say, generally in NLP, you have lots of different sub-communities. You have the sentiment analysis community, you have the machine translation community, the speech community, the question answering community, and so on. And the cool thing here is that really this model should be able to connect all these different communities, because we can essentially cast all these different problems as just question answering problems. So here's an example of a sentiment analysis. So we have this story, the input here. Despite the glowing reviews, this movie wasn't an especially engrossing experience. A fun sentence, and a lot in movie reviews you see a lot of these funny and interesting constructions where they actually have positive words, right? You have glowing reviews and an especially engrossing experience, so positive unigrams and bigrams, no really negative unigram or bigram, but the model still realizes that this is negative. And this is actually the most accurate model for sentiment analysis right now in the world, according to this benchmark data set from Stanford University that I actually published. I was a PhD student there a couple of years ago. But hundreds of researchers, including folks at Google, have since worked on that, and this model is the most accurate one. And there are really lots of fun examples that show that it's much harder to fool this model in many ways. So we could, for instance, say this movie doesn't care about cleverness, wit, or any other kind of intelligent humor. And ask again, what's the sentiment? And it realizes that no matter what you say here, all these positive things are actually negated. So, and again, magic here is, sure, we could write some regular expressions to try to capture some of these, but there are just too many to really be comprehensive with this. And I think, if we just change, the movie does care about these things, it is actually positive, right? So really like 3 character difference and completely different. So the model can be very sensitive to differences in subtle details. So that's sentiment analysis. We can ask other kinds of questions, such as what are the named entities? This is usually a very different kind of task for natural language processing. The first one is sort of logical reasoning, you need transitive understanding, facts, and so on. The second one is fuzzy understanding of sentiment and warm, fuzzy feelings. Now, named entity recognition is a sequence labeling task. So here we just trigger the answering module at the instead of at the very end, at every single word. And this is a very accurate model for named entity recognition. So here, it basically, in the NER, or named entity recognition task, we want to find all the locations, organizations, and people names, and just have those be labeled. Now, we can also ask for part-of-speech tags. It's more of a linguistics task, and the reason I'm bringing this one up is that it's exciting in that this is one of the oldest tasks of natural language processing. The data set is actually 22 years old, and thousands of researchers have worked on this task with a lot of different smart features and linguistic knowledge instilled in these algorithms, but the same model that got the state-of-the-art on the Facebook question answering data set and the state-of-the-art on sentiment analysis actually beats over 2 decades of NLP research also on part-of-speech tagging. And that's personally when I felt like deep learning is here to stay for lots of different sub-problems in NLP. There are different kinds of reasoning. Here's a temporal reasoning one where it was Mary before the bedroom, and basically, again, you don't need to tell it about time and so on, it just figures it out. You can also translate to French, just trigger it and translate to French. I think though, oh yeah, there you go. So again, machine translation, completely different sub-problem of NLP, but here you just give it as inputs the source language. The question is, or triggers like translate to French, entering training, the output is the other language. And so it's also a very accurate translation model. And because it really makes no assumptions about any of the language, and we don't need to do any specific engineering, it works really for any language. So it's also a very accurate model for Chinese sentiment. Again, it's just different inputs in terms of all the characters. The model figures out how to make right predictions. And this paper is on arXiv too, and it's linked on my website and the MetaMind.io website if you're interested. All right, so I hope I could show you that deep learning really made viable a lot of different tasks that require unstructured data understanding, be it speech or computer vision and image tagging or natural language understanding, and all the variety of different tasks that are behind natural language understanding. And with that, I want to thank you for your attention. And we have plenty of time for questions.
Just check that. How broad influence you need to classify for a new class?
That's a good question. So the question is, how many images do we need to train a new class? It's very hard to give.
But with the accuracy of more than 90%.
Oh, with the accuracy of that, that's a good one. It's an important distinction. I think it depends on how many classes you have, what the classes are, and how similar they are. So, for instance, if you have just two different classes and you want to separate sunflowers from cars, then unless you have lots of weird yellow cars and with funny sunflowers painted on them, that's a very easy task, and you probably only need a couple dozen images to separate sunflowers from cars. But now if you want to separate 50 different types of cars from one another, and you want to still have over 90% accuracy, then you really need to have lots of viewpoints that show, the various differences in these, subtly different classes. And there, the rough rule of thumb is to say 1,000 images per class is when, in most cases, we see over 90% accuracy. There's some, of course, also problems that are just very hard. Another test for that is if you can ask 2 people or 3 people to label your images, and they, in the majority of the times, actually agree with what the label should be, and then you have 1,000 examples per class, then you're usually in good shape. If even people disagree, then it's very hard to give the algorithm a good signal, and that often means also that the visual signal is ambiguous. So for instance, in the engagement prediction, that's a very hard task. Most humans can't do it at all. And even the algorithms only get into the 75 at most 80 kind of range, and it picks up on some obvious things like showing skin helps on social media and stuff like that. Yeah.
How does the last model that you showed us perform on text simplification?
Text simplification?
Yeah. And you didn't mention that at the text simplification so just I want to ask, what is the state of NLP in terms of text simplification?
So
This model as well.
So I guess, unfortunately, I don't have the answer because I've never ran the text simplification task on this model or with this model. So I don't have a definitive answer. But given that it does well on tasks like machine translation, I would think that it has enough sort of representational power to be able to do it. So it would be an interesting experiment to run.
How does the algorithm work to determine how engaging a piece of text is?
So basically, in this demo here, it has seen a lot of examples of above and below average engagement tweets. Of course, there it's very important to correctly pre-process your labels. You know, how many followers does this person have in the first place? What's the average engagement rate in this vertical, like movies versus cars versus, I don't know, real estate or something. Once you do this proper pre-processing, it actually just boils down to another classification problem to the algorithm. And in this case here, we chose not to use the dynamic memory network because people actually really want to see which particular phrases drive the prediction. And this model actually used to have also the state-of-the-art in sentiment analysis, where it made a lot of sense to have negation be sort of negating specific subphrases and things like that. But there, the dynamic memory network is actually more accurate in the end. But the recursive neural networks on these grammatical parse trees actually enables you to see exactly which phrases are the most important for, and which you might want to change also. So you can type in the sentence and then say, all right, maybe I'll move, take a closer look and replace it with another phrase and then get a different prediction out. But yeah, in the end, the way it works is really just by having a very large non-convex function over these tree structures that you're minimizing to lower your cross-entropy error for, similar to just standard logistic regression, but you learn lots of transformations, so nonlinear transformations of your inputs.
So do you learn these trees by your model, or they are pre-parsed?
So there's another model that also happens to be a recursive neural network that gives you the tree, but then you fix the tree and you just learn the prediction of the engagement on those fixed trees. Yeah.
Do you have any experience with / how does your model work with new forms of language? Say like rap music, they'll have whole entire new generations where you're like, you just say giga-da. Like, what is that, positive, negative, like, talk around that?
So the question is, how does it deal with various types of different language? And a lot of folks were very skeptical of saying, oh, can you even use parse trees for tweets? Because they're not very grammatical in many cases and so on. It turns out to still work fine, works just fine. And it might not get always the tree structure right, so some linguists would say this is not how I would analyze this tree grammatically, but it still gives you sort of key phrases that are important for your prediction. And in general, there's no magic. So if you, for instance, I think if you type in, let's see, this movie was funny. So that's positive, but this meat smells funny. It's actually neutral. So probably should be negative. Let's see, maybe we want to tell it that the sentence ends. All right, there you go. There's no other thing that comes afterwards. So it sees like the difference between different contexts, but if it had never seen that smelling funny is actually negative, it also couldn't get it right. So if you want to have it work particularly well on a specific type of data set, you do ideally want to also train with some of that kind of similar distribution. And you can start from the baseline model that just knows that awesome, wonderful, and great are all positive words, but then you can modify it and tune it to that specific domain. We actually have another tool where you just drag and drop text, and you can also create your own text classifier on the website.
What a relatively small size of data, and especially applied to natural language processing, and also more specifically to semantic learning. Is it advisable to use deep learning or more like traditional non-deep learning? For a small data, how deep learning has been so accurate when we have unplayed. What is the data set?
So the question is, should you use deep learning when you have a very small data set and a very semantic-like task? And I think the answer highly depends on whether you can use transfer learning, for instance, you have one domain where you have a lot of data, and then the general semantics are quite similar in your smaller domain where you have less data, then I think deep learning still makes sense. Now, if you can really only come up with a few dozen examples in your domain, and it's a very specific domain, there's no outside there's no way you will ever get thousands of training examples, then you might not want to use deep learning. But then again, who here deals with problems where you can only get a couple dozen examples? It doesn't, at that point you may as well just use humans to do it, right? So as soon as it's an important problem, you will probably have at least a couple thousand examples, and otherwise I would just continue doing it by hand. Yeah.
For algorithm functions in a query response format, have you ever developed a model that functions in a different way? So for example, for a query response, I want to buy a car, I'm not entirely sure what kind of car it is. The question that the computer will provide me, what brand of car are you looking for?
That's a great question.
Design a system like that? Is your algorithm functionality environment?
So that is actually a great, in some ways the question is question answering sort of isomorphic to dialogue systems. And in many ways the answer is yes. You can, whenever you have a fact here in the story, you can ask another question here, and then basically keep adding the questions that you had from before into your input story, and then have the model reason over everything, including the previous couple of questions.
So it's sort of state in the system from the previous questions that that's answered.
So to be honest, we haven't done it yet, but it's a very straightforward kind of extension. We haven't had an interesting data set to really train that kind of problem on. But I think there's no let me show you the paper. There's no sort of theoretical reason why you couldn't do this. Basically, here's and sorry for those who are not all deep into recurrent neural network type architectures, but basically this is sort of a zoomed in version of this dynamic memory network, and the main idea here is you have retrieve specific time steps and then reason over them multiple times to give it to an answer module. And now I think what you're describing would essentially just put after each question, the last question and the last answer as part of the input and then continue. So I don't see a theoretical reason why it shouldn't be extended to that. Good question.
So for your text extraction test, does your NER tagger also perform entity linking? That is to say, do you link the entities that you've recognized to some structured background knowledge, such as it could be your freebase when you perform this NER?
So we didn't train on sort of the entity disambiguation task, but we actually have also a model that links them at least to one another. So coreference resolution, where you can say, for instance here, what are the mentions? This is the task of coreference resolution. It's yet another NLP task that this model can solve. You can ask, basically by asking it or giving it different parentheses, you can ask Peter's sister is called Isabel. Is it coreference with Peter's sister? And then we'll essentially say yes, Peter's sister is called Isabel, so the answer here is yes. But it's not coreferent with Peter. So those are some examples of linking them between one another inside the sentence, but we haven't sort of done the mapping to figure out yet.
Have you guys tried playing riddles and have it try to, like, the way in my mind I'm looking at it is it goes back through, it's like, oh, well, I don't think it's green for that problem, and then it does research or something, then comes back and provides a more accurate answer.
So the question is, have we played with riddles in the model? The answer is unfortunately no. Not much money in riddles, unfortunately. But it would be cool. Pretty good research on it. Yeah.
Can you see one day, the feature of online chatting to help customers can be entirely replaced by machine?
I think so. I think there's some interesting work. And again, I think that the answer is yes for maybe 80% of simple questions. How do I plug my password in? I have a Windows machine, like how do I install this driver or something like that. But as you get more and more complex, and then you need to reason over this, and then you might not have the answers in your knowledge base already, you need to start Googling and like searching for something else and so on, then I think it gets harder and harder, and I don't think the models are yet able to recapture all the complexities that you could have in like driver and router and operating system configuration, and then reason over all the source code and like give you the right answer, right? So there's still limits, but I think even what we have right now if you have a relatively simple product, it should be able to answer a lot of questions. Okay.
I'm not very familiar with the subject, so my question might be very naive. What I've seen here and a little bit before is you get an answer for it works. You give it data, it tells you classes or other stuff. Do you get a similar insight into why? Or can you trace back what made it?
Yeah, so I think the answer is yes. So we, in many cases, have these descriptions. For instance, so on the visual side, we can bring it back to pixels, and on this one here, we can ask like, why do you think? Yeah, so we have this sort of explain button that digs into it, especially if it's a complex kind of query, and then we can ask it why did you actually. What are your reasoning steps to get to this answer? And that is, I guess, one way to have the model explain why it makes a certain prediction.
What I'm seeing, maybe it's not a question but a comment, I'm seeing what features might have been highlighted or picked up to make that assessment.
So the question is sort of what features are picked up. Well, I guess the tricky bit is we don't train the features, or we don't explicitly say these are the features. It has to learn it themselves. And so what you can do here is, for instance, look over, this is the features, for instance, for the sentence, despite the glowing reviews, this movie wasn't an especially engrossing experience. And what you do notice is that it picks up to put certain, like when you see a word with negation, for instance, it actually triggers that and changes one of these dimensions, and then continuously knows there's a negation in here. So that can change what comes afterwards. But that's the best you can do. All right, maybe one last question.
How well does the model do that you show with multimodal learning, like pictures and text descriptions? How well does it do with paraphrases that it didn't see yet?
So the question is, how well does the model do on this multimodal mapping task where we have images and sentences here with paraphrases. It actually, in some cases, does quite well. So we actually pre-trained the text part here based on so-called word vector representations that essentially capture co-occurrence counts, so the context of a word. So if you have the word horse and horsey, often in similar kinds of sentences and similar kinds of contexts, then the model can actually still find horses, even though it's only largely seen horses in the multimodal data set. It basically can use monomodality kinds of contexts from text to learn what, at least on the word level, what would be good synonyms. All right, thanks a lot. Those are great questions.